Okay, so today we'll continue on in Chapter 8 regarding hypothesis testing. Okay, and our textbook breaks hypothesis testing down into 4 steps. Okay, and so I'll put them here. Okay, so step 1 is to create your hypotheses. Okay, and that involves making a null hypothesis and an alternative. Okay, and so the null hypothesis always has an equal sign. Okay, and then the alternative is identical to the null, except the equal sign is replaced with something else. And then step 2, the book calls this prepare. Basically, we have to we're supposed to check hypotheses, okay, or check the conditions to use the central limit theorem. Okay, so a lot of our conclusions will be based on the use of the central limit theorem. So under step 2, we're supposed to check to make sure that the conditions to use the central limit theorem are met. Okay, we covered this already, in the midterm exam that you guys took, and so when I write problems, for the future, I'll generally write them so that the conditions are met. Okay, and so in real life, this is an important step to make sure that we can even use the central limit theorem in this scenario. But it's difficult to write exam questions where I set up a problem and I ask for things like find the p-value and make your conclusion, but haha, it was a trick because you were supposed to detect that the conditions weren't met, so there's no answer or something. So it's hard to do that, so I've separated it out, and I have one section where you check the conditions yourself, and you guys did that on the midterm. Most of you guys did very well on those problems, and then I'll have kind of questions on, can you do the process where the conditions are met. So under step 2, you check the conditions to use the central limit theorem. We're also going to select the significance level. And the significance level is our alpha. Okay. Sometimes it's specified in the problem, and if it's not, assume that it is 0.5. Okay, so step 3 will be, calculations. Okay, and we can kind of break this further down into a few components. Okay, so I'll call this 3A, which is going to be the standard error. once you figure out your standard error, figure out your test statistic. And as far as in Chapter 8, our test statistic is going to be a z-score, which is going to be the reality or the observed value and the difference between our reality and our expectation. So the difference between what we observed and what we expected divided by the standard error, okay? So again, under hypothesis testing, we're kind of comparing the reality versus the expectation, right? If reality and expectation matches up quite closely, then we have no reason to doubt our initial claims, okay? On the other hand, if the reality and the expectation are quite different, then that indicates to us that our initial claim is we've made a mistake. Okay. All right, so that's calculate your test statistic, and then finally convert the test statistic into a p-value. So you use the test statistic to get a p-value. Okay. And then lastly, we make a conclusion. Okay? And the conclusion is compare your p-value to the significance level to alpha, the significance level, and then decide whether to reject or not reject your null hypothesis. So if the p-value is less than alpha, then that means we reject the null hypothesis and we say we have evidence to support the alternative. Okay? And then on the other hand, if the p-value is greater than alpha, do not reject the null hypothesis, and we say we do not have evidence that the null hypothesis is wrong. Okay? It doesn't mean that the null hypothesis is true, it's just we don't have evidence that it's wrong. So these is hypothesis testing broken down into kind of our steps here, all right? And so let's work through an example together. Okay, so all right, so we'll say we've got a large tub of M&Ms, okay? It's our classic, our standby example here, all right? And then we want to know, is the proportion of red M&Ms over 15%. This is kind of the question we want to know. Okay, is the proportion we have in there, is it over 15%? That's what we want to know. Okay. So we get a random sample. We'll say of, I don't know, 150 pieces. Okay, and let's say 30 of them are red. Okay. So our sample proportion would be 20%, okay? And we're going to say, you know, does this provide evidence that the proportion of red M&Ms in the tub is over 15%. Okay. So at this point, we haven't done any math, but there's a couple scenarios here. One is the proportion of red M&Ms in the tub is actually 15%. And because of random chance, we happen to get a sample where 30 of them ended up red, where over 15% ended up red. Okay? And then the other scenario is that no, the tub actually has more than 15% red, and that's part of the reason why we're getting a sample of 20% red. Okay? So our data is n equal to 150. X is 30 red pieces, so the observed value that we get is 30 divided by 150, or a proportion of 0.2. Okay. Okay, so our first question will be, what are the appropriate hypotheses? Okay. Okay, so go ahead and pick out what you think is the correct hypotheses in this situation. Okay, so step one is to decide the hypotheses. Okay, just a few more seconds here to make your selections. Okay, 3, 2, 1, click, 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 click. Okay, I'm gonna hit stop here. All right, let's take a look. And indeed, C is the correct answer. Okay, so the null hypothesis is that P is equal to 15%, and the alternative is that it is greater than 15%, okay? And it really comes down to this question. Does this provide evidence that the proportion of red M&Ms in the tub is over 15%? So the fact that it says is over indicates that our alternative will have a greater than sign, okay? And we want to know, does our data provide evidence that the tub is 15% or more than 15%, okay? It's not going to be B, because B uses 0.2, which is actually the proportion that appears in our data, okay? And we can't, we use the data in such a way to reject the null and support the alternative, okay? And so if our null hypothesis, or if our hypotheses were set up under B, okay, all we would find is that our data kind of matches the null hypothesis, but that in of itself is not proof that the null hypothesis is true. It could just be a coincidence that that has happened, okay? All right, so I'm gonna just kind of clear this out so I have space to work, okay? And so, so now we'll do step 2, and just kind of for the interest of time, so step 2 is our check conditions. Okay, and I'll just tell you conditions met, okay? Okay, it's a random sample. 150 times 0.15 is over 10. 150 times 0.85 is over 10. And then if we assume this is a large tub with over 1,500 pieces of candy, all those conditions are met, okay? And then so under step 2, we'll go ahead and nothing is specified about the significance level, so we'll assume alpha is 0.05, okay? All right, so then for step 3, which is our calculations, we'll break this down into a few parts, okay? So 3A is our standard error. What is the standard error that we are going to use here, okay? The standard error is going to be P0 times 1 minus P0 divided by N, okay? The 0 is kind of like the 0 that appears in the null hypothesis, okay? So this just means use the P that appears in your null hypothesis. So P0 is the proportion, is the value from the null hypothesis. So in our case, we have 0.15 times 1 minus 0.15 divided by 150, okay? Notice this is different from when we did confidence intervals. When we did confidence intervals, we used p hat, okay? So note that in confidence intervals, okay, so this is it's a subtle change, but it can make a difference in the test. Okay, so we use P0, the value in the null hypothesis, and not our p hat. So when we do these calculations, we've got 0.15 times parentheses 1 minus 0.15 divided by 150. Okay, that's that, and then we're going to take the square root of this number, and I get 0.02915. Okay. Our test statistic is the comparison between the reality versus our expectation, or our observed minus expected divided by the standard error. Okay, so in this case, what we observed was a proportion of 20%, or here, let me do symbolically. Symbolically, we've got p hat minus P0 divided by the standard error. This is our Z, okay? And so we have 0.2, here, 0.2 minus 0.15 divided by 0.02915. And so I get a z-score of 1.72. Okay. And that's my test statistic. So z is equal to 1.72. Right? Okay, so at this point, we would go from our test statistic to a p-value. Okay, everyone so far so good? Okay, all right, and so so for 3C, we go from test statistic to a p-value. Okay, and so here are the rules. All right, so the rules here. Okay, if the alternative hypothesis has a greater than sign, okay, the p-value is equal to the area to the right of, I'm going to just write TS for test statistic. Okay. If the alternative has a less than sign, then the p-value is equal to the area to the left of the test statistic. And if the alternative has a not equal sign, then the p-value is equal to 2 times the tail area, okay? Where the tail area is to the right for positive test statistics, and tail area is to the left for negative test statistics, okay? Oftentimes, these are called one-tail tests, and this is called a two-tail test. Or two-sided test, or one-sided tests, okay? Okay, so in our problem, what was the our alternative hypothesis? Okay, so HA was that P is greater than 0.15. Okay, so this means our p-value is equal to the area to the right of z equal to 1. What did I say? 1.72 or something? Okay. So our p-value in this case is the area to the right of 1.72. Okay, and so at this point we just look it up in the table, and we go to 1.7, 0.02, and you get, I don't know, 0.9 something. .9573. Okay, and so the area to the right of that is 1 minus 0.9573. So our p-value 0.0427. 0.0427. Okay. Are we happy with this? We're happy. This is the best ever. Okay. So what does this mean? Okay. So so now we're going to make conclusion. Is it all right that I flipped the slide I just did? Conclusion. Our p-value is 0.0427. All right. what does this mean? Okay. So do you guys remember the definition of the p-value? P-value is the probability of observing our data or something more extreme if the null hypothesis were true. Okay? So what this means is that if the tub, if we could actually count them up, and if the tub actually was exactly 15% M&M, red M&Ms, okay? So if the tub were 15% red M&Ms, okay, then that means a random sample could produce a sample where 20% happen to be red, okay? A random sample could, just from random chance, produce a random sample where 20% or more are red. Okay? But the probability that that happens is only about 4.27%, okay? This happens probability 0.0427. Okay, so that is what the p-value is in the context of this problem. And I just kind of want to make sure that we are okay with this statement. This is it's important that we can kind of give an interpretation of the p-value in the context of this problem. Okay. So again, the p-value is the probability of observing our data or something more extreme if the null hypothesis were true. And what we're saying is that, yeah, could a random sample end up being 20% or more red just from random chance? Sure, it's possible, and it happens about 4% of the time, okay? And so now we're faced with a choice. We can say, all right, I think the sample that I got was just a result of random chance, okay? It happens 4% of the time. I could have been one of those 4%. Okay? The other option is, you know what? I'm going to say I wasn't part of that 4%, okay? And instead, I'm going to come to the conclusion that the percentage of red M&Ms in the bowl is actually, or in the tub, is actually over 15%. And that's why I ended up getting a sample where 20% were red. Okay? Do those two things make sense? Okay? So I'll write that. So we can say, okay, I still believe the tub is 15% red. Or the tub could be, I should say, not is, but that the tub could be 15% red. And, you know, I am part of the 4%, part of the 0.0427 that got a bunch of red M&Ms from by chance. Okay? Or we can say I don't think I am part of the 4.2.0427. Okay, I'm not part of the 4%. Okay, I conclude that the tub is over 15% red, and that is why my sample had a greater proportion of red M&Ms. Okay. Is this good? Okay. And so this is where that significance level comes in. Okay. So instead of just kind of dealing with our gut feelings and saying like, I think this is the case or I don't think this is the case, the significance level just kind of gives us a quick rule. And it says if it's bigger than the significance level, we're going to believe that it could have happened by random chance. And if it's smaller than the significance level, we're going to say it didn't happen by random chance and that the null hypothesis is wrong. Okay? So again, our p-value ended up being 0.0427, and we have a significance level of 0.05. This is our significance level. And so in our case, our p-value is less than alpha. Okay? So we say our data provides evidence that the null hypothesis is wrong. Okay, so we would say we reject the null hypothesis, okay, and we conclude that the proportion of red M&Ms is over 15%. So when your p-value is less than alpha, you're essentially saying, I don't think my data happened by random chance. Is this good? All right, let's see how much time we've got. Okay, let me talk about the significance level a little bit more in detail. Okay, and so we have so we said if our p-value ends up less than alpha, we reject the null hypothesis. Okay. So in that scenario, that last scenario, we said the p-value was like 4%, and so we decided we're going to reject the null hypothesis and say that the tub is actually over 15% red M&Ms. Okay? But is it possible that the tub actually is 15% red M&Ms and I just got this by random chance? Yeah, it's possible. And how often would I get a sample of 20% by random chance? We said about 4% of the time, okay? And so at this point, I could be wrong, okay? I could have made a mistake. I've come to the conclusion that the tub is over 15%, but there's also the possibility that I am wrong, okay? So, and so we call this mistake a type 1 error, okay? This is the mistake where, you know, I didn't do anything wrong with my calculations. What happened if I've made a type 1 error and the tub actually happened to be 15%, the only problem that happened was that when I took a random sample, just by coincidence, I happened to get a bunch of red M&Ms, and that led me to the wrong conclusion, okay? And it could happen just because of the random sampling process, okay? So if the p-value is less than alpha, we will reject the null hypothesis, okay? But this means, so I'm going to write, this means that the null hypothesis could actually be true and we just happen to get a random sample that produced a small p-value. Okay. And so a type 1 error, so the type 1 error is the thing they called it in the beginning, and as studies have advanced, we kind of gave it another name that you're probably more familiar with. This is called can also be known as a false positive. Okay, so type 1 error or false positive, this is we conclude that the null hypothesis should be rejected. Okay? In reality, the null hypothesis is true. That's a type 1 error. Okay? And our significance level, the significance level alpha, is equal to the probability of committing a type 1 error. Okay? So, I mean, if we choose alpha as 5%, then that means 5% of the time our p-value happens to be smaller than 5%, leading us to the wrong conclusion. Okay? So our significance level alpha is the probability of a type 1 error. Okay, on the other hand, we have something called a type 2 error. Okay, and this can be called a false negative. All right, and so here, our conclusion, we conclude not to reject the null hypothesis, okay? But in reality, the null hypothesis is false and should be rejected. Okay. And this is the probability of a type 2 error is beta. This is just a letter. Alpha is the first letter of the Greek alphabet. It's like the letter A. And beta is our second letter, so type 2, okay? That's actually where alphabet comes from. It's from alpha and beta, just pushed together. Huh? What's that? Yeah, is that exciting? Okay. All right, so we got this, type 1 and type 2 error. Okay, so let's, I'll just ask a last question here. Okay. So we're going to create the grid Okay, and your answer choices are going to be, this is the correct conclusion. Or here, we'll say A will be type 1 error, just to kind of, so we'll say A is type 1 error, B is type 2 error, and C is correct conclusion. Okay, so over here we will have reality, and over here will be our conclusion based on our data, right? Okay, so the reality could be the null hypothesis is true or the null hypothesis is false. This is what happens in reality. And as far as our conclusions go, we can choose to reject the null, or we can choose not to reject the null. Okay, so we'll call this box 1, and we'll call this, I don't know, box 2. All right, so this question, what is the answer that goes under box 1? Is that type 1 error, type 2, or is that the correct conclusion in box 1? Okay, get your clicks in. Under box 1. Okay, so get your clicks in. Okay, just a few more seconds, and then we'll do box 2. Okay, so I'm going to hit stop here. Okay, and then we'll just move on, and we'll do box 2. Okay, and then I'll give you box 3 and 4. Okay, so box 2. Okay, just a few more seconds. Get your clicks in for box 2. Okay, I'm going to hit stop. Okay, so box 1, this is a type 1 error. Okay, box 2, this is the correct conclusion. This box where the null is true and you choose not to reject it, that's also the correct conclusion. And then this box over here, this would be a type 2 error. Okay, we'll discuss more hypothesis testing on Friday, and we'll revisit this type 1, type 2 error stuff.